Hello everyone. Today we will talk about deep explanation in machine learning supported by visual method. This is a joint tutorial by Boris Kovalerchuk, which is me, and Ahmad and Ankur Teredesai, all of us from universities in the Washington state in America, which is on the west coast. We are happy that finally all these tutorials and conference are starting after all of this delay with COVID, but unfortunately it's still only online. So timeline of our presentation is here. We start at 9 a.m. on Japanese time, which is midnight in Europe, and 4 p.m. on the Pacific Northwest, where we are. So we will have an hour and a half for our first part of the tutorial. Then we will have a few more minutes for discussion and 5 minutes for break. And then at 10:40 Japanese time, we will start our next part, and again we will run it for 30 minutes. Then we will have time for question and answers, and we'll close at 12:15 Japanese time. So first question that we want to talk is why do we use black box machine learning models without explanations? The reason was well explained by Rubin. She tells us that it's exponentially harder to build transparent explainable algorithm from scratch than repurpose existing black box models, for example, for medical data. Therefore, researchers first let algorithm run and then try to understand later how it came to the conclusion. So the short answer for this question is that it's easy to repurpose than to build. The next question that we want to discuss, it's what is the scope of explicable AI? Some extreme view is here. It's recently published by Robbins in Minds and Machine. So he formulated the principle of explicability, where explanations by explicable AI are only fruitful if we already know which considerations are acceptable for the decision in hand. At first glance, it looks very normal statement without much severe conclusions. But however, if we go further, then the statement is the following. If we already have these considerations, then there is no need to use AI algorithm because standard automation would be available. An example was for declining a loan application. So indirectly, assumption here is that we have an algorithm which actually can justify declining the loan application, and we just can use standard computational tools like rule-based reasoning without any inductive discovery by machine learning. This principle of explicability for AI makes the use of AI redundant. So this obviously is a very extreme view on the problem, but the major question that we started still need to be answered. What is easier, making a black box and try to explain it later, or building an explainable model from scratch? because assumption always was that building explainable model from scratch, it's more difficult, like I already referenced Rubin statement. What we will do this tutorial, we will show that explaining black box can be harder than building an explainable algorithm from scratch, supported by a new efficient visual means. So we can actually reverse that situation, that building explainable model is extremely difficult. So there is a way to do this in a reasonable way. Thus, the easy first step, black box, makes the second step explanation extremely difficult. So what is this tutorial is about? We have two major questions here. How to build transparent explainable algorithms, in essence what is called today explicable AI. And the second one, how to explain predictions of black box algorithms, including deep learning algorithms. In the first one, we will review and analyze several approaches, including new lossless visual knowledge discovery approach based on general line coordinates. We developed those processes and we will describe them in the tutorial. In the second one, we will also review and analyze major approaches. A few words about ourselves. Like I mentioned before, all of us work in universities in Washington State, myself at the Central Washington University, Mohammad and Ankur at the University of Washington, and they also work for industry developing AI tools for medicine, and obviously where explainability is a critical issue. So we have 5 sections which we will cover, starting from foundations of interpretability, then go to discovering visual interpretable models, limits of visual interpretability in deep learning, then user-centric view of interpretability of visual methods, and open problems with current research frontier.
Hello, my name is Mohammad Aurangzeb Ahmad. I'm an affiliate assistant professor at University of Washington, Bothell, and also a research scientist at KenSci in Seattle, Washington. So I'll start off with talking about the foundations of interpretability. So before talking about interpretable models, it's important to define what kind of machine learning models exist. So they are white box or glass box models around which there's an explanation regarding how these models work and why they're making predictions. So think about models like decision trees, rule-based models, etc. And we can contrast them with black box models, which do not come with an explanation. We do not know how they work. Models like random forest, gradient descent models, and any and all deep learning models. So given that context, we can now talk about explainable AI or interpretable machine learning models. This is giving explanations of AI machine learning models to humans with domain knowledge, why the prediction is being made. The explanation should be in natural language, easy to understand representation for the domain expert. So in the equation on the right, the standard model Lagrangian would be comprehensible to a physicist, but not to vast majority of people in the world. So why do we need explanations? We need explanations especially for critical domains like healthcare, where suppose the model recommends doing a surgery, so the surgeon would want to know why that recommendation is being made. Certain countries, for example, the European Union countries have GDPR regulations where it's incumbent to provide, if needed, incumbent to provide explanations regarding machine learning models. So there's moral and ethical reasons to do so. And there are further nuances that one should be aware of while talking about interpretability. So in general, even if we look at the literature, then it's often assumed that regression models are interpretable. So, for example, consider a linear regression model on the left side of the slide. At first glance, it may seem that this interpretable model, so given some data, we have fit a line into this data, and the coefficients associated with the data represent or constitute the explanation of the model, and you can say that it's interpretable. While in reality, the relative importance of these terms may or may not be directly comparable. So suppose if this is a model which is predicting a medical outcome, and say one factor is measuring blood pressure and the other factor is measuring BMI or body mass index. Given that these are different units, different orthogonal dimensions, they are not directly comparable. Versus we can actually make any uh, linear model interpretable by different ways. So one prime way of doing that is by interpolating and converting that into a set of logical rules. So the visual on the right um, gives an example of how that can be done. And of course, if you have a very complex model with a large number of factors and different types of decision boundaries, then you can come up with a very complex model. An additional nuance to think about is what is known as simultaneity. So consider the model on the left, which is a decision tree model of making the following decision whether one should play golf or not. So one looks at weather conditions, amount of humidity, wind, so on and so forth. So one could say that that is an interpretable model, easily understandable. Uh, Versus if we consider the two decision trees on the right, now suppose it was the same decision whether to play golf and not. But decision tree A, because it's very complex, it's interpretable, and yet it's less interpretable as compared to decision tree. It's often stated that there is no formal definition of interpretability. In fact, that is not the case. There are few formal definitions. One that we prefer is as follows, worked by Muggleton and others, that we can define it in terms of comprehensibility and inspection time, where comprehensibility of a definition of output or program is defined with respect to a human population. To think about domain expertise, it's the main accuracy with which a human from that population, after a brief study and without further suggestions or insights, can use that information to classify new materials. Let's say randomly sampled from the definitions domain. And similarly, we can define the inspection time, linking it back to the definition of comprehensibility with respect to the mean time that a human from that particular population spends before applying that to a new material. And a similar generalization for textual complexity. A related question is how interpretable are interpretable models? So we can address that with respect to the domain. So is the answer with respect to the domain being considered? Um, is the explanation sound? That is, it actually adheres to how the model works, uh, versus is it complete? Does it encompass the complete extent of the model? What is the modality in which the prediction is being described, it's being explained? Domain specificity of interpretations corresponds to describing the model in terms of the ontology of the domain, and not using terms which are foreign to the domain where the problem is being solved. An example would be think about ratings that one gets in Amazon versus Uber. So on Uber, if someone has a rating of 4 out of 5, then that's cause for concern, versus in Amazon, a product with rating 4 is still a pretty good product. Uh, a related question with respect to the domain is the user centricity of the interpretations, that it has to be in the right language within the right context. So a number of domains and use cases. Uh, Researchers also talk about the Eli 5 principle, or explain it like I'm 5-year-old. That's in addition to making domain sense, it has to be expressed in a particular way. So think about the earlier example of from physics that we talked about. Another important distinction is Ante-Hoc versus post-hoc models. That is, uh, differences in terms of explanations where the models, the prediction and the model structure itself are the same versus whether they are different. Now we consider implicit explanations. To illustrate, consider the task of recognizing a boat in the image given here. So one could say that the model is able to recognize the boat based on a set of pixels that look like a mast, but then that explanation is not necessarily applicable to other boats in the image. Uh, and so to understand this, we have to bring in extra information to human domain knowledge, which is not explicitly present in the image. And especially if we talk about mission critical domains like medical imaging, if the radiologist cannot just look at the pixels and understand why the tumor is present, then we say that the explanation is explicitly not present. An implication of that observation is that is it that we are using black box models to explain other black box models? So the reason that we are able to identify the image as a boat given a certain arrangement of pixels is because it has distinct features relative to other arrangement of pixels. But that is the result of extra human domain knowledge that is not explicitly identified or present in the image. It is also important to delineate the scope of the tutorial. So we can talk about interpretability with respect to graphical models, reinforcement learning, natural language processing. However, if we look at models which are used in production, which are actually used in practice, then as a famous machine learning researcher, Andrew Yang, observed, 95% of those models are supervised learning models. And so that is also going to be the scope of our tutorial. Given its effectiveness and a hype associated with deep learning, it's also important to highlight its difference with traditional machine learning. For one, it does not require feature engineering. On the other hand, the trade-off is that it requires a large amount of data for it to be effective, and that's where it really shines with respect to more traditional machine learning methods. It's characterized by, especially in domains where it has shown incredible performance. You have models with literally billions of parameters, but models which work really well.
This section is about discovering visual interpretable models. Now we need to talk what is the visual interpretability. You see traditional textual explanation on the first row and visual explanations at the bottom. In visual method, for decision tree is the best illustration of the idea of visual explanation. You can trace any branch of the tree and see clear explanation because all attributes are in the domain terms. In the image processing, showing particular salient features is another obvious way to convince the user that it is a right way to do this. We will talk about this deeper. An alternative way using multidimensional representation of the data in a lossless way in the general line coordinate that we will talk later. The question which we want to discuss right now is why should we use visual thinking? First of all, we are not the first one, and the whole visualization community is well aware why it is efficient. It's interesting to note that many scientists declared fundamental role that images play in their most creative thinking. The list includes Bohr, Boltzmann, Einstein, Faraday, Feynman, and you see the list is longer, much longer. Albert Einstein was very specific, telling that words or language as they are written or spoken do not seem to play any role in my mechanisms of thought. The picture on the right shows the Indian proof of Pythagorean theorem with one single word, see. And if we try to reproduce the proof in the modern notation, you can see that it requires some algebraic operations and some extra drawing to make it very clear. in the modern term. So this demonstrates the power of visual thinking long time ago. The field is moving from visualization of solutions to finding solutions visually. It allows to leverage human perceptual capabilities and human abilities to adjust tasks on the fly. Why machine learning? To leverage analytical discovery that is outside of human capabilities. The first one, we cannot see pattern in multidimensional data by a naked eye and need help from machine learning. The examples of visual thinking above tell us that the major benefit of visuals is actually in discovering new knowledge, not just visualizing existing knowledge, including existing models. So when we want to go beyond visualization of existing models, we need to have a visual method for ND data representation that will preserve all ND information in 2 dimensions. Then we need visual method for model discovery in this n-dimensional data, and method to interpret visual data representation and models that are not internally interpretable, like we talked at the very beginning. And visual methods for 2 and 3D representations of ND data include 2 major classes of methods: reversible, lossless, interpretable. And this includes parallel coordinates, radial coordinates, general line coordinates, and their particular types like shifted, collocated, and so on. And non-reversible methods include principal component multidimensional scaling, multiple manifold TSNE, and many others. What is the visual discovery? We will illustrate with the following example with 2 attributes and 1 class. What would be the best guess about line fitting this data? The simple guess is that we have a linear discrimination function. In contrast, a quick look at this data visually represented immediately give us a visual insight of the model class of crossing 2 linear functions. This visual insight immediately gives us idea that any single linear function will not work, only pairs, which is shown below, and this is the advantage of the visual insight. While we were quite successful in the previous 2-dimensional example, but how we can do visual discovery in n-dimensional data, we don't have capabilities to represent all of them in the same way like we did with 2D. So the major issue basically of this presentation is to talk about the method, how we can do this without loss of information. Now we're coming to the major point of multidimensional data visualization. We cannot comprehensively see high-dimensional data. Method for lossless and interpretable visualization of ND data in 2 or 3D are critical to be able to discover multidimensional pattern. Unfortunately, often multidimensional data are visualized by lossy dimension reduction. Principal component analysis is a classical example. It only shows first 2 principal components, even if these principal components cover 90% of variability of all attributes. It's still only 90%, but it's not always the case. And variability of attributes not necessarily related to the issue of discovering how these attributes related to the target attribute. Alternative splitting ND data to a set of low-dimensional data pairwise correlation plots is good, but it's destroy integrity of ND data and leads to shallow understanding of complex data. An alternative to deeper understanding of ND data by visual representations of ND data in low dimensions without splitting a loss information is graph approach, not 2D point. And parallel and radial coordinates are examples of such method. So what we do in principal component analysis, we actually map, say, 10-dimensional point, 10 vector with 10 values to 2 values. In parallel coordinates, we represent each n-dimensional point as a polyline with actually 10 points connected by linear segments. And similar idea is used in radial coordinates. The only difference is that in parallel coordinates, all lines are parallel. In radial, they are radially located. This is an example of 4 different lossy visualizations of the same 9-dimensional breast cancer diagnostics data in MDS, principal component analysis, FDA, and support vector machine. Not only they differ visually, and different points may have a differently located relative to others, but features are artificially created. They don't have medical meaning. This is the most important, while the task is of medical diagnostics. And these observations are not a result of the bad design of those algorithms, but fundamental theoretical limitation known as a Johnson-Lindenstrauss lemma. To save time, and instead of going into formal details of this lemma, it actually tells us that only a small number of arbitrary ND points can be mapped to KD points of the smaller dimension k that preserve n distances with relatively small deviation. And the reason for this theorem is quite simple. 2D visualization space does not have enough neighbors with equal distances to represent the same ND distances in 2D. Results significant corruption of ND distances in 2D visualization. Let me give you one simple example. In 2 dimensions, center of the square has 4 neighbors, corners of that square. In 10 dimensions, the equivalent of the square is a 10-dimensional hypercube that has 2 to 10, 1024 neighbors. And obviously, mapping all these 1024 points to 4 points in 2D will definitely corrupt the distances. Formulation of the lemma defines the possible dimensions k less than n such that for any set of m points in high-dimensional space, there is a mapping to the lower dimension space with similar distances between mapped points in 2 spaces. This similarity is expressed in the terms of the error epsilon. In other words, this theorem means that the distances in the lower dimensional space will not be more than 142% of the original distance. So it will not be much exaggerated. However, it can dramatically diminish to 0 and corrupt knowledge discovery in low dimensional space, because cases which are actually far away from each other can have a 0 distance. Johnson-Lindenstrauss lemma shows that to keep distance errors within about 30% for just 10 arbitrary high-dimensional points, we need over 1900 so-called low dimensions and over 4500 low dimensions for 300 arbitrary points. The table on the right shows the tabulation of this data for different number of arbitrary points and spaces. There are different formulas and they give estimates for this lemma, but all of them are very similar, and all 3 are visualized in the diagram below. So the short conclusion is that visualization methods do not meet these requirements. Now we will talk about explanation for domain users. Major role of explainable AI is actually to give explanations to domain users, not only to developers, because explanations for developers it's only has an intermediate role, but the end goal is explanation for domain users. An explanation that a domain user could understand requires the same analysis as to build a case-based or rule-based systems. This is suggestions which made recently by a group of authors in 2020 when they discuss AI and law, how explanations can work in law, where obviously there is a very strong requirement to the explanations in law. And obviously this also includes identifying the terms that will be used in explanation. These authors provide an example with so-called SVM explanations for the European Court of Human Rights, and that explanation contained 20 most frequent words listed in the order of their weights obtained by SVM algorithm. And you see a list of these terms. And if you take a close look, you may notice that terms court and law could be in any decision and do not explain it. It's too generic. And the names of the months are artifact of that particular database. Obviously, another database will have different months. And what is important, that most of these 20 terms are not the terms of conventional analysis that will be used in such decision making. So these authors came to the conclusion that standard case-based or rule-based systems would be most practical way to solve this problem. In general, we agree with their position that we need to include terminology from the domain where the conventional analysis would be used, especially in the domain where such reasoning present, like in law. In the domains where there is no traditional reasoning, we may have a more relaxed situation, but for cases like law or medicine, there's definitely the situation like I described. Now we will talk about role and limitation of case-based and rule-based explanations. Now we will quote an experimental study by the authors listed below, done again in 2020, very recently. Of course, this is a limited experimental study, but they made a quite interesting conclusion of that study. Obviously, if we want to generalize them, we probably require more experiments, but even that relatively small experiment is quite instructive. So what they learned from that experiment, that rule-based explanations have a small positive effect on understanding, but jointly rule and example or case-based explanations persuade users to follow advice even when incorrect. So it's very strong statements. Again, we cannot generalize it for every possible task. And neither explanations improve human task performance compared to no explanation. And this is the most interesting part of the reasoning. In this study, both explanation styles only provide details relevant for a single decision, not for the whole rationality or causality of the reasoning. So in other words, these particular rules did not link them with causal domain theory. And now, next slide, we will talk about how generic actually their conclusions could be and what is their role in really explanations for the end users. So first of all, because focus of our tutorial is on visual methods and their role in explanations, we first will talk about how visual case-based and rule-based explanations actually help end users. First of all, we know that end users favor visual case-based and rule-based explanations as intuitive and quick perceptually, and visual knowledge discovery methods that we proposed construct both of them, case-based and rule-based explanations. So we will talk about them in this tutorial in detail. And what are limitations? Visual explanations suffer from the same problem as non-visual methods in terms of rationality and causality. They do not connect, they are not connected to the causal domain theory as a visual counterpart or the original not visual counterpart. So, and this is not specific for what we are talking about, but common to the current machine learning methods that do not use causal domain theory. Normally, in the so-called analytical machine learning, the term used, Tom Mitchell used first-order logic or inductive logic programming or general all relational methods allows to incorporate domain theories, but it's still outside of the today mainstream of machine learning. So, and why? The reason is quite simple. Many domains do not have rich formalized causal domain theories. So it's not a question that people object to use them and make rich, but simply we are not at that place yet. The next question is, can we explain machine learning without causal domain theory? The short answer is yes. If a link between a class and attributes is based on a common sense definition, not on the physical cause. For example, we recognize a bird type. A bird type is defined by a set of features. If, for example, if a golden feather and a red forehead are present, then the type is European goldfinch. The link is not by the cause, but by definition. A user see a group of salient pixels and name them by knowing features under three conditions. User know names of those features. Salient pixels or group of the pixels correctly capture them, these upper level features, and the users can recognize these features in the original image and match them with the salient pixels. So the system which only shows these groups of pixels gives us a quasi or quasi explanation. Why? Because the rest need to be done by a user. All these 3 points need to be completed by a user, which we just listed. Moreover, if a method to find these high-level features is a black box itself, then we explain black box with a black box. Thus, the full explanation is coming from the user doing 1-3. Now we will talk about explanations for tasks with classes by definition, not by cause. So we had a previous example with the bird category or type. Now we talk about digits, recognizing of digits from popular dataset MNIST. obviously, each digit is given again by definition. There is no cause here. And the example which we see here shows the digit 3, which produced heat maps by gradient multiplied by input saliency map, and produced by deep learning neural network for digit 3. And what is important and interesting in this example is the difference between outputs not only for the category 3 but also for category 7 and 5. As it is well known, the deep learning algorithms compute output signal for each of these possible outputs, and ones which has a maximum output is actually outputted as a recognized result. And now you can see that red ones indicate the correct salient pixels, or better say expected in the digit 3, and the blue which are not expected. So what we can see in the map for digit 7, that the bottom blue part is not expected to be in 7, and the right blue part on the top is not expected to be on the digit 5. And this is actually very well defined features that separate 3 from 7 and 5. So that's explaining why it is not 7 and why it is not 5. And the authors of this paper, Gupta and Arora, they actually developed new output results, not only by maximum, but actually combining and outputs. So the output is here, where most critical characteristics of digit 3 is shown in the middle, in the bottom, and on the top, relative to comparison with 7 and 5, or maybe even more of the cases. Now we will talk about new lossless generalized coordinate approaches, algorithms, and case studies. We have two fundamentally different approaches, lossless and lossy approaches. In the lossy approaches, like we already talked about, we use point-to-point mapping, n-dimensional point to two-dimensional point, or n-dimensional to three-dimensional points, and then interactive discovery of 2D patterns in the visualization. In the lossless approach, we actually use ND data and ND pattern, convert them losslessly to 2D, and try to discover 2D patterns in 2D without loss of original ND information. This is an example of one of such algorithm which we called GLCL algorithm, with L stands for linear. Consider a four-dimensional point, 1.8, 1.2, and 1. And we design 4 coordinate lines which are not all parallel but under different angles. And then we put those values on these vectors. So for example, x1 is equal 1, so the vector will be blue one on the top of that black coordinate x will be equal to 1. Next one is a 0.8, 1.2, and so on. So now we have these 4 vectors, and then we shift the second vector to the end of the first one, third one to the end of the second one, and the fourth to the end of the fourth one. In this way, we build a polyline and then project that polyline to below. And next, we will show what kind of properties we get with this. The projection of the point here on the horizontal line will produce us a new point. And now you see the blue point is here, and for another polyline we have another blue point. And then we can do similarly with symmetrically mirrored points from with other values. And let's assume that blue ones belong to one class and the red ones belong to another class. Then we can build the yellow line that would separate these two classes. Of course, the question is how we set up angles that way so the points of the lines are separated. This is a process of optimization of the angles, and we can show that it's actually create the linear separation of two lines if visualize a multidimensional linear discrimination without any loss of information. This is a real case when we use 9-dimensional Wisconsin breast cancer data, and you can see that all blue cases from one class and red from another class allowed to make a prediction quite accurately with 96% linear separation between classes. And only one cancer case was recognized incorrectly, because we are really always concerned that not to miss cancer cases. So we deliberately put only one case here, while we can get high accuracy, but because we wanted to decrease the number of cancer particular errors, not just general accuracy. So how it was done? By simply shifting this yellow line to decrease the number of undesirable points. Is actually, you can see it here. This is another example. As you have seen in the previous slide, all these polylines heavily overlap with each other, and the human cannot see individual lines. Another approach, when we draw each of these polylines in the separate image, like you can see here, images from one class, images from another class, and you can see visually quite significant differences between them. And to discover this pattern, what happened, we actually created those images and put them to the convolutional neural network, CNN, and asked that neural network actually discover this pattern, and it was done with high accuracy, 97%. Line coordinates more specifically, because we mentioned several times, but all of the previous examples were just examples. In general, the idea of general line coordinates that we allow the coordinates be to follow to any direction, be straight lines, be curved lines, and so on. Now you can see parallel coordinates where all of them are vertically parallel. All coordinates are in one horizontal line, or all of them go radially, or some of them are vertical, some horizontal, and even curvy lines connecting them. Another example of general line coordinates, when coordinates are located on the sides of the rectangle. The first coordinate is here, second is here, third, fourth, and so on, and those curves actually represent each particular point. Then we can use so-called circular coordinates, where coordinates are curvy. So this is a coordinate x1, coordinate x2, x3, and x4, and those coordinates can be put in the space, so it's simulating the geospatial representation. So they serve kind of a glyph in the particular location, where the center of the circle also indicates a geographic location. Similarly, you can get a pentagon coordinate locations or locations them in the triangle. This slide summarizes different types of general line coordinates in two-dimensional space. In more general way, drawing n coordinate in a variety of ways: curved, parallel, unparallel, collocated, disconnected, and so on. Now you can see the long list of this type of coordinates. It can be generated where all of these coordinates are located in 3D space in the same way, can be curved, parallel, unparallel, collocated, and disconnected. Later on, we will show applications of the 3D general line coordinates for financial applications in the market. This slide illustrates the idea of collocated paired coordinates, where we have a 6-dimensional point 5, 4, 0, 6, 4, 10, where first pair 5, 4 is located here. Then the second pair of coordinates again located in the same coordinate here, and the third one 4, 10 located here, so they are connected, and as a result you have a representation of a 6-dimensional point as a just polyline with 3 points and 2 edges. Similarly, can be designed shifted coordinates, where first pair coordinates is here, second is here, and third is here. And there are several modifications of them. Later on, if we will have more time, I will explain them. This is another set of examples of general line coordinates. The first one is based on the radial coordinates and collocated, so it's a combination of them, where coordinate x1 and x6 are collocated, x2, x3 collocated, x4 and 5, and as a result, here the 6-dimensional point is now represented as 3 points connected together. Similar idea allowed actually to represent very high-dimensional points. For example, here you can see 192-dimensional point built in this way. Another way, it's a generalization of a circular coordinate to elliptic coordinates, where 4-dimensional point is losslessly represented as a pair of points A and B. If somebody will be interested, I will talk about this detail, but we have a special presentation on the advantages and application of the elliptic coordinates in AI session, so we are welcome to come to know more about this. This slide illustrates not only the variability of the putting coordinates, whatever location and directions we want to them for the coordinates, but different ways to build graphs using these vectors. All of them generalize those methods which I already shown you above. The advantage of this approach is that it can be quite uniformly programmed and just adjusted for setting up particular way of location of coordinates and methods to joining them. Statements showing what are advantages of different general line coordinates. First of all, they allow to preserve all ND distances which we have between points as the distances between 2D graphs. Second one, they show that the number of points needed to losslessly represent them is 2 times smaller than in more traditionally well-known parallel coordinates. The idea of visualizing the pattern in the simpler way is illustrated here. For example, in parallel coordinates, because of the abilities to shift up and down of coordinates, and we can make the red pattern straight, which is making it much simpler for humans to recognize, and then to reordering these coordinates, make a green pattern is going up, which is making for human much easier to simplify see. And this is another multiple ways to do simplification of the visual patterns. This case study of the world hunger data illustrates advantages of the collocated coordinates. It's on the right, you see multiple countries with different years when the index of the hunger was recorded. It's obvious that in one of the countries the situation is improving, another one it became worse. So while it's relatively easy to see pattern on the few lines on the top, but then they become cross each other and the pattern is not that obvious. In contrast, the same data visualized in collocated paired coordinates much more cleaner, visible what is going with different countries. This case study illustrates the advantages of shifted coordinates. Let's consider health monitoring with parallel coordinates and with collocated paired coordinates. So we have 4 attributes here, 2 for blood pressure and 1 for cholesterol and 1 for pulse. And we have 4 people here presented, and you can see the pattern. You either can interpret this as 4 different people, or you can consider this as one particular person, which starts with particular status, which is red, where his or her parameters are not good, and then going to the improved green status, what the doctor actually wants to have the patient achieve. Okay, and the same is visualized in the shifted coordinates. First 2 coordinates represent the blood pressure, systolic and diastolic, and the second pulse and total cholesterol. Then the scale and distances between coordinates is taken that way, so that the desired point, 170, 120, 60, and 190 is represented as a single green point, and the other points are represented as arrows. And now we can see how the human is progressing from the original state to the target state. It's very simple, clear visualization, which does not need special training, and people can use it quite effectively. 4 figures in this slide show Challenger space shuttle disaster data with 23 flights that preceded Challenger flight. The top 2 show traditional visualizations in time series and parallel coordinates, and bottom show in collocated paired coordinates. While first 2 do not show the specific pattern, the last 2 show that all lines go up, only 2 lines differ. 1 line go down and 1 horizontal. This is exactly 2 cases which were most similar to the situation in the day of the Challenger flight. So this data could be clearly indication that disaster could be actually avoided if they would be analyzed. This example illustrates lossless visualization and 48 and 96 dimensional data and humans' abilities to discover patterns in such high dimensional data represented with proposed combination of radial coordinates and shifted paired coordinates, which I defined and explained above. So you can see here the first row with this what we call the stars, and second row is for parallel coordinates, and you can see that people were able to find patterns in the first one, such as presented on the right, and were much more difficult for them to discover pattern in parallel coordinates. They were able to do this a little bit better with traditional radial coordinates, but not as good as with our CPC star coordinates. This experiment shows the experiment with 160 dimensional data, and humans were able to again discover patterns of two classes. So you see here the samples from the green class and red class, and people need to classify them. And in parallel coordinates, it's extremely difficult. People practically failed. In contrast, were successful with the proposed method. So both of them lossless, but very different losslessness is for human. In one case, human can discover pattern. In second one, people cannot. This is another experimental data, real 170 dimensional data mask from University of California Irvine machine learning repository. Again, you can see some patterns visible in stars and practically not visible in parallel coordinates.
So after the discussion of lossless methods and some new research in that area, so we move our attention to more traditional and lossy methods to create the contrast between the two. We start with one of the most widely known methods, the PCA, or the Principal Component Analysis method. The main idea behind this method is very simple yet elegant. That is to account for the variance of data in as few dimensions as possible using linear projection. And there are variants of PCA which use different assumptions. So coming back to the simplest version of PCA, so the idea is that the first principal component is the projection direction that maximizes the variance of the projected data in that dimension. The second projection is orthogonal to the first and maximizes variance in the projected data, so on and so forth. That said, PCA has certain limitations. So as you can see, it starts with the assumption that the angle between the dimensions, so that is capturing the most amount of information. But that may not always be the case. Um, it may be the case that sometimes most important information is not orthogonal. There are other lossy methods like TCNE, which have become extremely popular over the last decade. The main idea behind this is to visualize high-dimensional data in 2 or 3-dimensional maps. For a large number of data sets, it works really well in terms of creating a symbol map that reveals structures within the data at multiple scales. And especially if you have data which we can demonstrate that it lies on several different but related low-dimensional manifolds, then it works really well in practice. To illustrate the limitation of these traditional lossy methods, so we again consider the breast cancer data that we had talked about earlier. So using 3 different methods, PCA, TCNE, and Laplacian eigenmaps, we project them in 2 dimensions and 3 dimensions. And here we see that none of these methods are able to separate out these classes across these dimensions. So why is that the case? Why are we observing this? So it's because methods like TCNE, PCA, and others in this family, they actually do not preserve all the information features, the initial features in the data. So if given n dimensions, they convert them into 2 to 3 artificial features or dimensions, which do not have a direct information in the domain. And so going back to what we illustrated with the GLC methods, so we can actually think of that as an alternative where all n dimensions information are preserved and the information clutter that we observe in these methods, especially if we go to higher dimensions, that is not observed in GLC. To illustrate, we revisit another well-known data set, the MNIST dataset for digital digit recognition. So if we visualize the digits which are recognized or which are visualized by embedding of these methods, specifically in this case TCNE, then yes, it is able to identify and separate out the images. However, from a semantics perspective, what does that actually mean? Well, it turns out that they actually do not correspond to any quote-unquote features in the real world. In fact, even the author of TCNE, Matin, he warned against using such generalizing statements regarding assigning semantics to groupings which are recognized by TCNE, that they may not actually have a certain meaning that we assign to them in the original n-dimensional space. Hence, to summarize, it's basically this lack of domain interpretation which is present. We now consider the problem of visualizing association rules. So in data mining, association rules are implications of the form if X then Y. So these are not logical implications. So these are based on co-occurrence of certain things in the data. So for example, consider, let's say, a transactional data based up of things that you buy in grocery shops. So an implication would be if eggs, then butter, if eggs, then milk and butter, so on and so forth. So one challenge with association rules and trying to make sense of them is that if you have a large enough data, then you may end up with millions of association rules. So how do you make sense of these? So one way to do that is with visualizing the rules. So based on their support or confidence, which corresponds to their relative occurrence with respect to one another and with respect to the overall data set. So in the visual, that what we are seeing over here is that we can visualize the association rules with respect to their support and confidence and how many rules fall under a particular category, what is present in the right hand versus left hand side of the visual. So it's a good way to summarize such rules. But even with this, as we can see, if there are sufficiently large number of such items present, then it would become difficult to make sense out of these rules. An alternative way is that, especially if your search space is relatively smaller, then one can visualize these rules with respect to relationship graphs. So in the visual, based on our work, we described relationship between certain outcomes, certain chronic conditions in a healthcare data set. And so we can make a sense out of how different factors like chronic kidney disease, malnutrition, ulcers, how they are related to one another and with respect to the outcome. Yet another way is to visualize these association rules is a more interactive visual discovery-based approach. That is, first we discover all the relevant association rules, and then we start deleting dimensions which are irrelevant to the association rule or even to the dimensions of our interest. And then we can visually explore these in the form of parallel coordinates, interactively changing these based on what the end user selects. Additionally, if you look at more recent methods of making sense out of machine learning models, then post-hoc explainer methods like tree explainer methods have become quite popular, especially applicable to tree-based models, where the idea is that these models measure the direct interaction effects between the different features, and dependencies between them. And so based on a number of empirical experiments and even deployments which have been done based on these methods, then it has been shown that they more closely align with people's intuitions. That said, they do have the limitations that other lossy methods have. So similar families of techniques, especially for rule-based methods, have been explored. So one such example is the rule matrix, which is used for understanding classifying using rules. So the idea is that for many of these methods, given arbitrary models, it is possible to extract rule out of these models. Uh, and one can vary thresholds and look at inputs, outputs, and see how the output changes, what are the different factors which are going inside uh, these models with respect to the particular outcome. So one limitation of many of these models is that these are post hoc models. So the explanation that one produces, it may or may not correspond to how the model actually works.